other structures are found in the integumentary system? We have the epidermis and dermis of the skin. Attaching the dermis to the rest of the body is the hypodermis. Hypo indicates below, so this is found below the dermis, acting as a foundation for the skin. It attaches it to the underlying structures like muscle and bone, and also allows blood and lymphatic vessels, nerves to pass through it to and from the dermis. It's composed of loose and adipose connective tissue containing roughly about half of the body's fat. Thinking back to the function of adipose tissue, it is a good padding that protects the body and also acts as insulation, preventing heat loss from occurring. Because so much adipose is found here, the hypodermis can be used to estimate total body fat content. This differs between females and males pretty significantly, with roughly 12% of total body mass and 3% of body mass being healthy for females and males respectively. There's quite a large range. Age is going to play a pretty big factor. In both women and men, fat content goes up as we age, so healthy range also increases. And diet also, of course, is going to influence how much adipose is found here. So here again, we can look at this familiar diagram of the skin. The hypodermis, also called the subcutaneous layer, is found here. So lots and lots of these adipocytes found here that have a droplet of triglyceride or lipids in them. And then these larger vessels, nerves, are going to move up and down through this region. Another accessory structure is hair. Hair is found everywhere on the human body except for a few select places: the palms of the hands, soles of feet, lips, nipples, bit of the genitalia, and the very distal segments of the fingers and toes. So almost everywhere. Hair is going to be held in epithelial tissue of the epidermis called the hair follicle, which extends down into the dermis, completely surrounding the hair root and the hair bulb. So it kind of looks like you're dipping a corn dog through the epidermis down into the dermis, and all that epithelial tissue of the epidermis just follows the hair down. We'll take a look in a second. The hair itself is divided into a couple different areas. What we call hair commonly is the hair shaft. This is a long, flexible strand of dead keratinized epithelial cells that extends up above the surface of the epidermis. This is the visible part of the hair. The hair root goes down into the epidermis and dermis below the skin or scalp. So, like the root of a plant is below ground, the root of a hair is below the surface of the skin. The root terminates in a bulbous region called the hair bulb, which is the thickened base of the root. This contains living cells analogous to the stratum basale. Cells dividing here are going to cause the hair to grow, as they are pushed into the hair root and the hair shaft. This hair follicle is going to hold the hair within it, giving hair its shape and texture. It's also crucial for repair of the skin because the epithelial cells here are great at regenerating, and they can give rise to new cells in order to heal damaged structures of the dermis. Here we can see that hair shaft above the surface of the skin, then following the root down to the base. The epidermis follows it, creating this hair follicle around the root and the base in the dermis. You can see it's like the epithelial tissue of the epidermis. And here, zooming in on it, there is a structure called the dermal papilla in the hair bulb, which we'll talk about in a second, but it's like the capillary loop of the papilla of the papillary region here that we talked about in the skin. Blood vessel lives here to nourish the living cells of the hair. You can also see melanocytes, right, which makes sense because melanin is found within the hair as well. Hair grows kind of like the epidermis grows. Just like the cells of the stratum basale undergo mitosis and older cells are pushed up into the more superficial layers, hair is going to be produced in the hair bulb, where again we have that hair papillae with the blood vessels to give oxygen and nutrients to these living cells. And the hair is going to grow longer as these cells divide to add cells to the bottom of the hair at the hair bulb. Older cells are pushed up into the root. However, growth differs from growth of cells in the epidermis because while cells grow in the epidermis continuously, here growth occurs in cycles. Growth cycle followed by resting cycle. The growth cycle is pretty straightforward. It's when growth occurs. Mitosis causes the cells to divide and push older cells up into the shaft. Keratinization occurs here as well to produce very keratinized cells in the root and shaft. This is followed by a resting phase where the growth stops and the hair is just held in place within the follicle. Typically, the next growth phase is going to push that old hair out. We lose about 90 scalp hairs a day, for example. And that just means that we're at the start of a new growing phase and a new hair is growing to replace the one that we lost. Depending on the hair, these cycles are very different. Scalp hair grows for years, 3 years, and then it rests for a couple years, whereas eyelashes grow for just 30 days and then rest for 105. While we start off with melanocytes producing melanin here, as we age, melanocytes are going to grow fewer. They produce less melanin. Gray hair is a result of less melanin, and as we lose melanin entirely, we have just air bubbles trapped in the hair shaft, which results in white hair. Each hair follicle is associated with a bit of muscle called the erector pili muscle, which is a complex name, but breaking it down, pili or pilus always refers to hair. For example, bacteria have hairs all over them, which allow them to adhere to surfaces, and these are all called pili. Erector sounds like erect, right? So this is a muscle that makes the hair stand erect. This is what it does when it contracts. It forms goosebumps and causes the hair in the follicle to stand up straight. You can see it here, erector pili muscle attached to the follicle. Now, what does this do? What's the function of this? We can think about when we get goosebumps, really 2 times, when we're cold and when we're scared. When we're cold, if we had more hair, having the erector pili muscles contract would allow that hair to trap air closer to the body, forming another layer of insulation for us. So, for example, animal covered in hair stands up, becomes thicker, so we can conserve body heat close to the body. The other time that our erector pili muscles are stimulated is when we are threatened, when we're scared. And this causing the hair to stand erect can make a hairy mammal look bigger, so appear more of a threat, or less of a target, than a smaller animal. And again, for us, this doesn't do anything, but for most mammals which are covered in hair, this will have a function. Another accessory structure found with the skin is the gland. And we have a few different types of glands. Most broadly, glands can be divided into sebaceous glands versus sudoriferous or sweat glands. Sebaceous glands are connected to a hair follicle, so they're not independent. They're always found right next to a hair follicle. They release an oily substance called sebum, which empties into the hair follicle, then is released at the surface of the skin, where it's going to moisturize and lubricate the hair and skin. This prevents drying and cracking. Cracking would allow bacteria and other harmful elements in, reducing the protective quality of the skin. We don't want that, so that sebum helps with that. It also has a mildly antimicrobial property and fights against some bacteria. Like our epidermis houses or rather feeds dust mites, another animal really likes sebaceous glands in the sebum it produces. That's the face mite. The microscopic mite here causes no harm whatsoever, called Demodex. Interestingly, there's shared DNA amongst the face mites found in families. So, families that stay together, their face mites get to stay together too and form families. They look a little scary, but again, no harm for this mite. Sweat glands or sudoriferous glands come in 2 types, the eccrine gland and the apocrine gland. Eccrine glands, think the letter E, right, for eccrine. Eccrine glands are found everywhere, all over the body, particularly numerous in the palms and soles. They are independent structures that open directly into their own sweat pores, releasing sweat at the surface. Eccrine sweat is mostly water, with a few salt secretions and just a trace amount of waste. They are activated by heat. So as our temperature increases, eccrine glands will release that watery secretion, which then evaporates, bringing our body temperature down. So when we're out for a run and get really sweaty, it's these eccrine sweat glands that are doing that. When we get really hot and get sweaty, same deal, eccrine sweat glands. So these are the glands that function in thermoregulation. Eccrine sweat glands are also stimulated by emotional stress when we're anxious. So when a polygraph is trying to catch a liar, one of the elements, one of the variables that's measured is conductivity of the skin. And that's because really what we're measuring is eccrine sweat gland activity. So the idea is if we're nervous, then these glands are stimulated, we'll be sweating more, and all that sweat is going to change the conductivity. Now, if you're taking a polygraph, particularly if you're in a police station taking a polygraph, you're likely pretty nervous anyway. So are these tests even valuable? Are they accurate? Well, not really, right? They're only detecting whether you're nervous or not. So they actually aren't admissible in court. Not much use for a polygraph. It's only seeing if someone is upset, anxious, is scared. Apocrine sweat glands are more limited. They start out as eccrine, but then turn into something else, apocrine, due to hormonal changes during puberty. They are only found in the armpits or axillary region and the pubic area, and they start to produce a much thicker secretion that's rich with organic substances. This secretion itself is odorless, but those organic substances are very attractive to the fauna of the skin. The bacteria that live on us love to snack on it, and as they metabolize it, it releases an odor that we know of as Biol, body odor. So maybe you can think apocrine sweat glands make us smell like apes. And here we can see the sebaceous gland opening into that follicle there. The apocrine sweat gland, which almost looks like eccrine, right? But the duct is coming all the way up and then eventually meets up with that hair follicle as well to release its secretions. The eccrine sweat gland is an independent structure which has its own duct that allows it to release its watery secretion here, which is the only gland whose secretions function in thermoregulation. Nails are also part of the integumentary system, also somewhat similar to the epidermis of the skin. They are thin plates of layers of dead keratinized stratum corneum cells with an especially hard, resilient keratin. The nail is composed primarily of the nail body. This is the visible portion of the nail. The nail root is what extends proximally underneath the skin. Again, just like the root of the hair goes underneath the skin, the root of the nail is invisible underneath the skin. Cuticle isn't technically part of the nail. It's part of the stratum corneum tissue that covers part of the nail body. The nail matrix is the base where the nail root terminates. So kind of like the hair bulb, the basal layer of the epidermis. This is where we have living cells that are dividing, allowing the rest of the nail to grow. The nail bed is also living tissue, which attaches the nail to the finger. And then finally, the lunula, the lunar for moon, this is the part of the nail matrix that's visible at the base of the nail. You may, as you look at your nails, see this at the proximal part of the nail bed. You can still see it. Some people have a fairly large lunula, some people very small, and some people can't even see one there at all. So highly variable. And this is our nail here, a couple different views of it. Here, this is what you see when you look down. The nail body, lunula, cuticle, much softer than the nail itself. And then the nail root is invisible, hopefully, unless something horrible has happened to your finger. Now, if we cut our finger in half, we can see the nail root terminating at the nail matrix, where nail growth occurs, and then the nail bed, which is extending underneath the whole nail body to attach it to the finger, the rest of the finger. Both our nails and our hair, majority is composed of dead tissue, but they are still good indicators of the overall condition of our body. So poor nutrition, for example, is going to influence the growth of both hair and nails.